Welcome to Applied Thermodynamics course. This is week 9 of the problem solving session. This is the last module of the gas power cycles. So previously we saw about a Brayton cycle, how it's used and the alternatives arrangement to get a increase efficiency, to get a more work output out of it. So that was in the previous week. This week involves using the Brayton cycle in the jet engines, and how instead of power you just like in car you use an internal combustion engine, just like that you use it in a aircraft. So how it works, and you will see now some numericals how to solve those. So before starting, we'll see how what are the jet engines. So basically jet engine is just like an internal combustion engine. So normally in car you have internal combustion engine, in jet engines you have inlet air coming in, and the aircraft moves at some velocity. So it's at some velocity. You have uh, air which is coming in the opposite. You have a relative velocity. So air is having some velocity. It enters the engine. So what happens is initially it has some velocity. So initially you have some diffuser. So what this creates is the velocity is converted into some form of pressure energy initially to create some pressure. So the velocity is converted into pressure, and then it will have some initial velocity which is converted to some pressure and velocity in goes in, and then you have a compressor, turbines in the combustion chamber, and then turbine, and then a nozzle. So there is a 4 stages happening, similar to what a Brayton cycle. You have 4, so similar to you have here too. So one, for initially you have a compression happening in the initial diffuser, where the velocity is getting converted into pressure energy. So that's the initial compression, similar to, and then again in the compressor your pressure is increased. So that's the second process in the compressor. So after compressor, what you do is you do an heat addition. So you spray fuel and you combust, and it's in the combustion chamber. So you increase the energy of the air. So after that, what you do is you expand it in the turbine. So what happens is the turbine needs to generate some work. So you use this work to run the compressor. So because you have to give some work to you have to do some work to run the compressor. So this is generated with the turbine. So then what happens is after expansion in the turbine, what you will do is you will pass it through a nozzle to expand it. So and this is converted into velocity, higher velocity, and it come out as a jet. So this will have some velocity which is greater than what it had an initial velocity. So this change in velocity will create an force which will move the aircraft. So what happens is initially you need here what is generally is done is there's a conservation of linear momentum which is being conserved here. So we know from Newton's law that any object that will like to be in its state, so it doesn't want to change. So if you want to change, you have to create apply a force. So in this case, if you see the aircraft is there, and there is some velocity of air coming in, and a higher velocity stream which is going out. So when that is going out, there is a change in velocity. So this will create an opposite direction force such that the aircraft moves. So in this process, you have the momentum being conserved. So that's what happens. So next is this engine. You can classify into 2-3 types. So one is a turbojet, then you have a turboprop, and then you can also has a ramjet engine, and there's also a pulse type engine. So in a turbojet is what I explained now, how the jet engine works. So initially is what the velocity of aircraft is moving. You have initial velocity of air which is going into the engine in the diffuser. There's increase in pressure, Then in the compressor you are again pressurizing the air, and then moving in the combustion chamber you are increasing energy of the air, and then it's expanding in expansion and then coming out of the nozzle. So this is a typical phenomena which is happening in the turbojet engine. Then the variation of that is the turboprop. Why we need to go to a turboprop? So if you see turbojet engine, uh, it's good, it has at a higher efficiency is more at a higher speeds, but it cannot create enough thrust during the start. So in the case of turboprop, you can get that initially. What happens in turboprop is similarly, just like in the diffuser, there is this velocity which is coming in, getting pressure raised. This effect is called as a ramjet, and then after in the diffuser where the pressure is increased, you compress it again in the compressor, and then combustion chamber and the expander. So now the expander, what it does is it not only drives the compressor as in the case of turbojet, but also a propeller which is at the front. So uh, a larger amount, say to 80% of energy is spent in running the compressor and the propeller, and 20% of it is passed through the nozzle energy. So what happens is in a turbojet your thrust was created just because of the jet which is coming out at high velocity. In turboprop it's because of the jet as well as the propeller which is at the front. So this two drives the engine or the aircraft. So this has a better initial thrust for a takeoff. It's better than the turbojet. And the other other type of engine is the ramjet engine. So ramjet engine, what happens is the previous engines which I talked about in the initial phase where the velocity is getting converted into pressure. So it's because of the Bernoulli's principle, right? So similarly in the ramjet engine, what happens is in turbojet and turboprop you have compressors. So, but in ramjet engine you don't have a compressor. So this is more engine is more efficient when it's at high speeds. It goes at high speeds because then you have higher velocity of fluid coming in, then you can increase in pressure, and that it can go out. So that's the idea. In this case what happens is you don't have there is no moving parts here, there is no compression expander. So velocity of fluid which is coming in, the velocity is converted into pressure energy, then there's a combustion happening which increases the energy of the air, and then what you do is you expand it in the nozzle. So this ramjet kind of engines are used in supersonic planes and so on, but you need additional some engines to create an initial takeoff, because this works better at the higher velocities. And the other one was the pulse type engine, pulse jet engine. Here that is similar to an IC engine where it's not there is no continuous work being generated. So here too there is no continuous work being generated. So it's just an can say a variation to the ramjet. So initial fluid air which is coming in is pressurized, and there's a valve which will close, and the air inside will be combusted and it will be exhausted in the nozzle. So this valve will keep on closing and opening in the each of the process. So this is not a continuous process, but it is similar to an internal combustion engine where you have one expansion stroke which creates power. Here too there is a cycle of power generation. So these are the types of engines, and if you see, these are similar to the operation is similar to Brayton cycle. So if you don't consider the nozzle and diffuser, the other three parts is the compressor, combustion chamber, and the expander, which is similar to the Brayton cycle what we use. This diffuser and nozzle are to create that initial thrust and initial pressure and energy. So this is similar to a Brayton cycle, and we'll see how some MCQs and numericals in those jet engines. So that first one is A jet engine works on the principle of conservation of dash. So a jet engine works on the principle of conservation of dash. A, mass. B, discharge. C, momentum. D, energy. So as I told previously that the jet aircrafts work in the conservation of momentum. So the answer is momentum. Uh, as I told previously, according to Newton's, that any state of inertia will try to be in its state of rest. So if you see, if you don't consider there is some air coming in, because and the velocity which is going out air and what is coming in, there is a difference. So consider there is air going out of the aircraft at that relative velocity. So if some air is going out in the relative velocity, so we previously what the aircraft we considered it was at rest. Now there is a velocity going out. So this is not similar. So what we will try to do is this will try to move forward so that the total momentum is conserved. So that is what happens. So there is a velocity going out to create that creates an thrust which will move it forward. So the jet engine works on the principle of conservation of momentum. So the next is in working condition of turbojet engine, velocity of air entering the engine is dash, then the velocity of exhaust gases leaving the engine. So we know that the velocity of air entering is it will be lower compared to the exhaust gas. So or else there will be no difference in velocity and it will not create a thrust for the aircraft to move forward, or to create a instance when it's flying, for the aircraft to be at a uniform velocity, you need that thrust to remain same, because of the velocity you will also have drag forces on the aircraft which will try to pull it. So that will end this thrust will cancel out and it will maintain uniform velocity. So I told to create that thrust there should be a difference in velocity. So when the velocity of jet is more outside and it's going out, the one which is coming in should be at lower velocity, or else you will not get that initial thrust for the aircraft to move. So it should be lower. So the next one is, through the intake of an aircraft, the process of converting the kinetic energy of the entering air into the pressure rise is known as ram effect. It's a true or false statement. So it says that intake of an aircraft, the process of converting the kinetic energy of the entering air into pressure rise is called as ram effect. It is true. So this ram effect happens in all types of engine, and this phenomena is used largely in the ram jet engine. So this ram effect is true, that initial velocity which is air which is there, it has processed some kinetic energy. That kinetic energy, part of it is converted to a pressure energy, so it will create a increase in pressure. So this effect is called as a ram effect. So this is true. So the next is, the air standard cycle for a turbojet engine is based on reverse Brayton cycle, diesel cycle, Brayton cycle, and Joule cycle. So this is as I already explained how this is similar to the gas turbine cycle. So this is these two turbojet engine works in a Brayton cycle. So the answer is option C. So if you see the components for Brayton cycle is, you have compressor and combustion chamber and expander. The compressor and expander turbine work in isentropic process, and combustion you have constant pressure process. So a similar process is used here too in the turbojet or engines, jet engines. So the answer is option C. The next one is afterburners in aircraft engines are used to decrease the thrust of turbojet engines. It's a true or false statement. So the answer is true. Sorry, decrease. Sorry, this is false. So afterburner, yeah, you use afterburners. What happens is after a compressor and combustion chamber, you increase the energy of the fluid. You expand it part of it. To create more thrust, what you'll do is after expansion, you spray some fuel. You combust again. So this is similar to a reheat phenomena, which you do it in Rankine and Brayton. So this is similar to that. So after expansion, what you do is you spray some fuel, you combust again to increase the energy of the fluid after raise the temperature of the and pressure after expansion, and then you pass it through a nozzle. So this creates more thrust compared to the previous one. So the afterburners are used to create more thrust. So this statement is false. So the next one is the turbojet engines mainly employ axial flow compressors. So this is true. So you know axial flow will flow through through the axis. So this is true. So moving on, isentropic efficiency defined in terms of dash and ram efficiency expressed in terms of dash respectively are two methods by which the efficiency of intake system are analyzed in a turbojet engine. So we have options of pressure rise and temperature rise, and B temperature rise, C temperature rise and pressure rise. So if you see isentropic efficiency if you basically define for compressors and expanders, and you express it terms of the enthalpy change. So what enthalpy change is happening in the compressor and what it could happen in the isentropic way. So that's how you compare the isentropic efficiency. So in this case, ideal case, what you assume is your specific heats are constant. So you can express that enthalpy in terms of temperature. So isentropic efficiency is defined in terms of temperature. So that is in case of temperature rise. And then ram efficiency, as I told previously, you converting kinetic energy into pressure energy. So that will be defined in terms of temperature rise. So the answer is option C, isentropic efficiency in terms of temperature rise, and ram efficiency in terms of pressure rise. So the next question is propulsive efficiency of a jet engine dash with increase in aircraft velocity. So A decrease, B increase, C remains constant, D none of these. So this will increase. If you see propulsive efficiency is defined as thrust power divided by propulsive power. So this can be expressed, thrust power is just thrust into the velocity, and propulsive power is the change in your kinetic velocity square, mass into. So this will you can simplify it in terms of velocities, just the velocity. Air Ca is the velocity of air which is coming in, and Cj is the velocity of jet which is going out. So if you see you can just see, if you see Ca increases, your propulsive efficiency will go up, because there is a twice in the numerator, so it will create an increase in efficiency or propulsive efficiency of the jet engine. So if aircraft velocity increases, the propulsive efficiency will increase. So the next one is, which of the aircraft engines do not use compressors? So the next one, so I see we have seen the different types of engines. So ramjet, turbojet, turbofan. So out of this, the only engine which does not use compressor or there's no moving parts in the engine is the ramjet engine. So the answer is option A, ramjet engine. So next question is, in jet engines, the gases expand to ambient pressure in a jet nozzle. So this is true. After compression, after expansion, you pass that through the nozzle, and even in the case of a turboprop, some amount of is being passed through a nozzle. So the statement is true. So we'll see how to solve this. Air enters a turbojet engine at 320 meters per second at a rate of 30 kg per second. So you know mass flow rate of air which is entering and its velocity, and exits at 650 meters per second. So you know that jet velocity too. So relative to the aircraft, so the thrust developed by the engine is, so we have some values. The thrust values 5 kilonewton, 10 kilonewton, 15 kilonewton and 20 kilonewton. So if we see, we know the velocity of air which is coming in v1 is 320 meters per second. Velocity of fluid jet which is going out v2 is 650 meters per second, and we also know mass of air, the rate which is coming in, so 30 kg per second. The thrust is nothing but the change in momentum of the air happening, so that will create the thrust. So thrust is the force which is acting on the plane. So that is, force is nothing but change in momentum, rate of change of momentum. So rate of change of momentum is nothing but the mass flow rate into the change in velocity. So m dot into v2 minus v1. So we know mass of air which is coming in, the rate which is coming in 30 kg per second, and velocity is also we know 650 and 320. So difference is 310. Sorry, 330 into 30 will come out to be 9900 Newton divided by 1000 equals to 9.9 kilonewton. So divide by 1000, which I did is to give answer in kilonewtons. So this is coming out to be 9.9 kilonewton. So which is close to 10 kilonewtons. So answer is option B. So next we'll see some numericals, how to solve this. So first we'll see a turbojet engine consumes air at the rate of 60.2 kg per second when flying at a speed of 1000 km per hour. So they have given the inlet velocity of air and also inlet rate of air which is coming in and the speed. So we have to calculate the exit velocity of the jet. Exit velocity of the jet when the enthalpy change for the nozzle is 230 kilojoule per kg and velocity coefficient is 0.96. So then second is fuel flow rate in kg per second when air fuel ratio is 70:1. Thrust specific fuel consumption. Then thermal efficiency of the plant when the combustion efficiency is 92% and the calorific value of the fuel used is 42,000 kilojoule per kg. Then we have to calculate propulsive power, propulsive efficiency and overall efficiency. So we'll see how to solve this. So some of the values required are already given. We'll see how to solve this. So what we know is the rate of air consumption or the air coming in is 60.2 kg per second, and the enthalpy change in the nozzle is 230 kilojoule per kg, which is given. So exit velocity of the jet when the enthalpy change for the nozzle is 230 kilojoule per kg, that is given. Then velocity coefficient is given 0.96. It's just like the efficiency defined for the diffuser or the nozzle. And air fuel ratio is 70:1, and combustion efficiency is 92%. Then calorific fuel of value of fuel is 42,000 kilojoule per kg. Then aircraft velocity is given as 1000 kilometer per hour. So we'll convert it to meters per second. So 1000 into 1000 converting into meter divided by 3600 or 60 into 60 to second. So it will give me 277.8 meters per second. So this is the aircraft velocity, or it will be equal to the velocity of air which is coming in to the engine. So these are all the parameters which we know. Then we need to calculate first is exit velocity of the jet. So exit velocity of jet, it can be calculated by doing in steady flow energy equation across the nozzle. So it will come out to be enthalpy plus velocity square by 2. There is in the nozzle there is no heat addition and work addition, so that all will be 0. It will be equal to h2 plus velocity square at state 2 divided by 2. So if you see velocity, can assume that velocity is one of it is negligible at the inlet of nozzle, and exit will be at a very high velocity. So that will come if you remove that. So the velocity square at state 2 will just be equal to the change in enthalpy. So you can reformulate it and you can get the velocity at nozzle at state 2. So this velocity coefficient is nothing but velocity which you can have but what you have. So the ratio, so there is a efficiencies of 0.96. So Cj, velocity of jet, will be equals to the velocity coefficient into root of 2 into enthalpy change, and enthalpy is in kilojoules, so multiply by 1000 to convert it into joules. So we know the velocity coefficient is 0.96, so into root of 2 into 230 kilojoules, that is change in enthalpy, into 1000 to convert it to joules. So this will come out to be 651 meters per second. So this is the velocity of jet which is coming out of the engine. So now we have found out the velocity of jet. So the next is to find out the fuel flow rate in kg per second when air fuel ratio is 70:1. So we know air fuel ratio, and we also know the rate of air consumption, so we can straight away find out the fuel consumption. So fuel consumption is nothing but rate of air consumption divided by air fuel ratio. So rate of air consumption is 60.2 kg per second. So divide by 70 for air fuel ratio. So this will come out to be 0.86 kg per second. So 0.86 kg per second is the rate of fuel consumption. So we have found out what is required in step 2. Then third is we need to find out the thrust specific fuel consumption. To find out thrust specific fuel consumption, first we need to find out the thrust force or thrust produced. So that is nothing but the change in momentum, the linear momentum, so which we calculated in the previous example as well. So the change in momentum or rate of change of momentum, so rate of mass into change in velocity, the jet and the air. So m dot a is already calculated 0.86 kg per second. We know the velocity of air coming in, which is 277.8, and we also know the velocity of the jet, which is 651 meters per second. So we just have to substitute in this equation 60.2 into 651 minus 277.8, which will come out to be 22.47 kilonewtons. So that is the thrust which is generated. So now what is asked is to find out thrust specific fuel consumption. So thrust specific fuel consumption is just like what we saw in the previous module and the Braden cycle, just like brake power specific fuel consumption. It's just now fuel consumed for that for a kilonewton or for a newton of for thrust generated. So the amount of fuel consumed for a newton of thrust to be generated. So fuel consumption, so thrust specific fuel consumption is fuel consumed divided by thrust generated. So fuel consumption which we have calculated 0.86 divided by thrust is 22.47 kilonewton. So substituting that, will come out to be 3.828 into 10 power minus 5 kg per newton of thrust per second. So this is the thrust specific fuel consumption. The next is the thermal efficiency. So thermal efficiency can be calculated as work output divided by heat supplied. So that's thermal efficiency is what amount of work is generated out of the heat which is supplied. So gain in kinetic energy per kg of air is what is the work output, or so it will be equals to 1 plus mf by ma into cj square minus ca square. So after that you can this is the change in kinetic energy of the air, and then divide by heat supplied. Heat supplied is nothing but the mass of fuel into calorific value, or multiplied by efficiency if there is some combustion efficiency. In this case the combustion efficiency is given as 92%, so we'll multiply that. Here cj square it's divided by 2 because it's change in kinetic energy, so the 2 is in the denominator. So now this can be simplified assuming 1 plus mf by ma as 1, because your air fuel ratio will be very small, fuel air ratio will be very small. So if you say 1 by 70, it will be very small and close to 1 value. So you can assume this 1 plus mf by ma as 1, or it will be equal. You can substitute that as well. Here I have assumed 1 plus mf by ma as 1. Then we know all the values required. We just substitute. Cj is 651 square minus Ca is 277.8 square divided by 2. That will give me the change in kinetic energy of the air. Divide by mf by ma, the mass of fuel, divide by ma into calorific value is 4,000 to 42,000. It's kilojoule, so multiply by 1000, and the combustion efficiency is 0.92%, so 0.92. So this will come out to be 31.39%. So thermal efficiency of the engine is 31.39%. So the next one is to find out the propulsive power. So the propulsive power is nothing but the change in kinetic energy of the air. Here this was the change in kinetic energy. If you see work out with change kinetic energy of the exit will be your fuel plus air, and inlet will be air. Here we are considering just the air, so that's the difference here. So propulsive power is equal to m dot a into the change in kinetic energy of the air. So outside it will be jet minus the air inlet. So m dot a cj square minus ca square by 2. So we know all the values. We will substitute, and it will come out to be 10.43 kilowatt. Then we can find out the propulsive efficiency. Propulsive efficiency, you can straight away use the propulsive efficiency in terms of velocity, the simplified version, or you can find out propulsive power, which we have already done, and we can also find out thrust power. Thrust power is nothing, you have to just find out thrust power into velocity of air. So that can be found out. We have already calculated thrust, so we have to just multiply with air and we can find out thrust power. So we'll straight away substitute in terms of velocity here. So we know both the velocities, so 2 into air velocity divided by jet plus air velocity. So this will come out to be 59.8%. So the propulsive efficiency is 59.8%. So next is the overall efficiency. Overall efficiency is nothing but propulsive power into your thermal efficiency. You can find it, you see, if you multiply propulsive efficiency 0.598 into 0.3139, you will get 0.1877. So we can find out overall efficiency by multiplying propulsive efficiency into thermal efficiency. The other way around to calculate is thrust work or thrust power divided by heat supplied by fuel. So we can do that. We can multiply. So this will come out to be substituting that values will come out to be 0.1878 or 18.78%. So this is same as propulsive power, propulsive efficiency into thermal efficiency. So moving on, we have another problem on turbojet. So a turbojet engine is traveling at 216 meters per second. So it's straight away given in meters per second. In air at 0.78 bar. So inlet pressure is 0.78 bar and minus 7.2 degrees Celsius. So air first enters the diffuser, in which it is brought to rest relative to the unit. So initially it is brought to rest and then it is compressed in a compressor through a pressure ratio of 5.8 and fed to a turbine at 1110 degrees Celsius. The gases expand through the turbine and then through the nozzle to atmospheric pressure. The efficiency of diffuser, nozzle and compressor are each 90%. Then the efficiency of turbine is 80%. The pressure drop in combustion chamber is 0.168 bar. So these are all what's happening in engines. The values are all given. The efficiencies, the pressure drop and the temperature are all given. So now we need to find out air fuel ratio, the specific thrust of the unit, the total thrust if the inlet cross section of the diffuser is 0.12 meters per meter square. So specific thrust, air fuel ratio, total thrust, and then that's it. So in calorific value to be assumed of 44150 kilojoule per kg. So let's see how to solve this. So you see, we know initially the aircraft velocity is 216 meters per second. So the air which is coming in, it is at a temperature of minus 7.2 degrees Celsius. So converting into Kelvin, we will get 265.8 Kelvin. And the inlet air pressure is 0.78 bar. The pressure ratio in the compressor is 5.8 and the temperature of the gas entering the gas turbine, so state 4, the turbine, I think the plot is wrong. Just a second. Okay, the process will be somewhat similar to this. So you have initially diffuser. So from state 1 you are having some velocity, and then you are compressing it. So the velocity, kinetic energy is converted into pressure and it is brought to rest. So the velocity becomes 0. That's what it means. So state 2, that's what's happening in diffuser, and the diffuser has some efficiency, 90% efficiency. So 1 2 it will happen isentropically, but in this case instead of 1 2 it will be 1 2 dash. And then with the compressor there is a compression ratio of 5.8. so the compressor it will be ideally it should be 2 dash 3, but compressor also has an efficiency of 0.9. so we'll follow path 2 dash 3 dash, and then at state 4 the energy, this is at temperature 1110. In that the turbine is expanding with it should be 4 5 isentropically, but the turbine has efficiency of 80%. so it follows path 4 dash 4 5 dash, and after that it passes through nozzle which also has an efficiency of 90%. so 5 dash 6 dash, this is the process of the jet engine. So now see how to solve this problem. I'll change this plot here, there's a mistake made, so I'll change this plot. And so we know all the efficiencies and the values. So first is we need to find out the air fuel ratio. So for an ideal diffuser, what happens if you do an energy balance across the diffuser, your state 2 is there is no velocity, that's what it's stated. The gas the first enters the diffuser in which it is brought to rest, so relative to the unit, so velocity is 0. so there is no kinetic energy, just the enthalpy h2 equals h1 plus velocity at the inlet ca square by 2. you see there is no heat input or work input into the diffuser, so that all terms, this is steady flow energy equation. From there we can find out the temperature, as the enthalpies are just function of temperature assuming an ideal fluid. So we can find out temperature, which will be T2 minus T1 equals Ca square by 2 Cp. Enthalpy is Cp T2 minus T1, enthalpy difference. So from this we can find out the temperature at state 2. So state 2 will be state T1, we know temperature at the inlet, and because of the kinetic energy, state 2 it's energy enthalpy is increasing, and so that's the temperature. So we can find out the temperature at 2. so T1 is 265.8 plus the velocity is 216 meters per second, so 216 square divided by 2 into Cp is 1.005 for air into 1000 kilojoule per kg, so multiply by 1000. so this will give me temperature at state 2 as 289 Kelvin. So but this is for an ideal diffuser, but this is not the case in case of an actual diffuser. So actual diffuser efficiency is H2 minus H1 divided by H2 dash minus H1. So you can find out H2 dash minus H1 as H2 minus H1 divided by the diffuser efficiency. This can if you see can also be expressed in terms of H2 minus H1 is a Ca square by 2. so if you express this in terms of temperature, you have to just substitute that, and we can find out T2 dash. so T2 dash is T1 plus Ca square by 2 Cp into diffuser efficiency. so this will come out to be 291.6 Kelvin. so previously ideal case it was 289 Kelvin, so now the temperature is 291.6 Kelvin. so now we know the temperature, so we can find out the temperature pressure. so we are assuming this as an isentropic process or adiabatic process, reversible adiabatic. so we know T2, we know T1, so T2 by T1 equals P2 by P1 raised to power gamma minus 1 by gamma. We know T2, we know T1, and we know P1, the pressure at inlet, and gamma is 1.4 for air. So substituting that, we can find out that pressure at state 2 is 1.044 bar. So this is the pressure. We cannot use T2 dash because that pressure will be same, but because of the diffuser efficiency, just the temperature is rising, but the pressure will remain same. So next is across the compressor. So we know the pressure ratio, which is of 5.8. So compressor will also have a reversible adiabatic process. So we can find out the state 3 temperature. So we can straight away use T3 by T2 equals P3 by P2, which is compressor pressure ratio, raised to power gamma minus 1 by gamma. So substituting the values, we can find out T3 as 481.7 Kelvin. So now the compressor is now not ideal, so it has efficiency of 0.9. So we can find out as the enthalpy So compressor efficiency defined as the enthalpy change in the isentropic process divided by the actual process. So compressor work by actual work. So T3, if you write in terms of assuming that Cp is constant for the ideal ideal air, so Cp can be cancelled out and enthalpy can be expressed in terms of temperature. So the compressor efficiency can also be expressed in terms of temperature. So if compressor efficiency is T3 minus T2 dash by T3 dash minus T2 dash, so T3 dash will be equals to T2 dash, just reformulating to find out T3 dash. So T3 dash will be 502.8 Kelvin. Then in case of the combustion chamber, you are supplying some energy, which is equal to the calorific value into mass of fuel. This will create change in enthalpy of the fluid, so which can be expressed as Ma plus Mf into Cp by T4, which is the enthalpy at after combustion, and before combustion the energy of air is Ma Cp T3 dash. So from here we can find out ratio for Ma and Mf. So we know calorific value, we know Cp, we also know all the temperatures. On substituting, we find out that the mass of air by mass of fuel ratio is 48.34. So from here we have found out all air fuel ratio which was required. The first question is to find out the air fuel ratio. The next question is to find out the specific thrust of the unit. So to find out specific thrust, in the problem it's given that pressure drop in the combustion chamber is 0.168 bar. So after state 4, at state 4 inlet to the turbine, the pressure is at 5.88 bar. This is the pressure at inlet of the turbine. So now assuming that the turbine drives the compressor and no other so whatever work is generated in the turbine is going into running the compressor. So the work generated in the turbine equals to the work consumed in the compressor. So Cp T3 dash minus T2 dash is the compressor work, and Cp T4 minus T5 dash is the turbine work. So Cp gets cancelled out, so we can find out T5 dash straight away. So T5 dash is 1383 minus 502.8 minus 291.6, so it will come out to be 1171.8 Kelvin. So this is T5 dash. So now to find out the isentropic temperature, so we can use the turbine efficiency to find out T5. So T5 will come out to be 1119 Kelvin. So now using this we can find out the pressure at state 5 or the exit of turbine, assuming a reversible adiabatic process. So T4 by T5 equals to P4 by P5 raised to power gamma minus 1 by gamma. So we know temperatures, we know pressure at state 4, so we can find out state 5 pressure as 2.8 bar. So using this we can find out the temperature at state 6 at the exit of the nozzle. So assuming that the nozzle is the process reversible adiabatic isentropic process, so state 6 temperature is 813.75 Kelvin. So now using this, and we know that nozzle is not efficient, so it is efficiency is of 90%. So using that we can find out the actual temperature at state 6, which will be equals to T6 dash. So T6 dash is equals to T5 dash minus efficiency of nozzle into T5 dash minus T6. So using this we can find out the efficiency, substituting efficiency and temperature, we can find out the temperature at state 6 is 849.5 Kelvin. So now we have found out all the temperature and pressure required. So we know the exit temperature and pressure. So the velocity at the exit of the nozzle is, to find out that, we can find out, we need the enthalpy change. So Cj equals Cj square by 2 equals change in enthalpy. So we can find out jet velocity from there. So we have simplified it, the values, and so it will come out to be 44.72 root of h5 dash minus h6 dash. So if you so here Cp should be substituted in terms of kilojoule. So if you take a root of 2000, it will come out to be 44.72. Root of 2000 because 1000 from kilojoule and 2 by Cj square by 2, that too. So multiplied by root of 2000 will come out to be 44.72. So 44.72 root of Cp, the change in temperature. So we now know the actual temperature out and the temperature. So substituting temperatures, so we will get the jet velocity at 804.8. So now we know the jet velocity, we can find out specific thrust. So specific thrust is nothing but 1 plus mf into Cj. So we know fuel air ratio. So fuel air ratio is 1 by 48.34. 1 plus mf by ma, 1 plus mf by ma into Cj. So Cj is 804.8. So this will come out to be 821.45 Newton per kg of air. So this is specific thrust. So now we need to find out the total thrust. To find out total thrust, what we need to find out is the mass of air. So specific thrust into mass of air is gives me total thrust or thrust. So for finding out volume of mass of air, we need to find out the volume flow rate into the density. The problem is given that the diffuser is of 0.12 meter square. Cross section of the diffuser is 0.12 meter square. So we know area into velocity of the inlet velocity will give me the volume flow rate. So 0.12 into 216 meters per second will give me 92 meter cube per second. So this is the volume flow rate of air which is coming in to the diffuser. From this we can calculate the mass flow rate. So mass flow rate is nothing but volume into density. Density is P by RT, or using ideal gas equation, ma is P1 V1 by RT1. So P1 is 0.78, the inlet pressure, into 10 power 5 because it's in bar, converting it to Newton per meter square, into 92, sorry, 216 into 0.12, sorry, 216 into 0.12 will give me 25.92. This mistake, volume flow rate is 25.92. Substituting volume flow rate 25.92 divided by 0.287 into 1000 into 265.8 is the temperature. So substituting that will give me 26.5 kg per second. So this is the mass flow rate, and the total thrust generated is mass flow rate of air into specific thrust, which we have calculated. So 26.5 into 821.45, which will come out to be 21.77 kilonewton. So moving on, the next question is, the following data pertain to a turbojet flying at an altitude of 9500 meter. The speed of the turbojet is 800 km per hour, and propulsive efficiency is 55%. The overall efficiency of the turbine plant is 17%. So propulsive efficiency is given, to turbine total efficiency, overall efficiency is given, velocity is given. So density of air at 9500 meter altitude is 0.17 kg per meter cube. So drag on the plane 6100 Newton. So drag is equal to the thrust, because if you assume that aircraft is moving at constant velocity, so if it's in constant velocity, the aircraft will generate some thrust. So there is no net force acting on the plane. So because it's in constant velocity, it's not accelerating. So it's not accelerating means there is no force acting on the plane, net force. So the thrust which is generated in the aircraft will go somewhere. So this is will be equal to the drag on the plane. So the drag force will be equal to the thrust force. So drag on the plane is 6100 Newton, so which is equal to the thrust force generated by that plane. So next is assuming calorific value of the fuel to be 46,000 kilojoule per kg. Calculate absolute velocity of the jet, volume of air compressed per minute, diameter of the jet, power output of the unit, and air fuel ratio. So we'll see how to solve this. So we know velocity is 800 km per hour. So converting that into meters per second, I'll get 222.2 meters per second, and I know propulsive efficiency is 55%, overall efficiency is 17%, and density is 0.17 kg per meter cube, and drag on the plane or thrust is 6100 Newton. So now absolute velocity of the jet is nothing but the jet velocity minus the air velocity. It's kind of the relative velocity relative to the air. So what is the jet velocity? That is the absolute velocity. So the reference is the air which is coming in. So the absolute velocity of the jet is Cj, velocity of air, jet minus velocity of air. So how do we find out? We know air velocity, and we know propulsive efficiency, which is 55%, and we know propulsive efficiency can be written in terms of velocities. So propulsive efficiency is 2 times air velocity divided by jet velocity plus air velocity. So substituting that, we can find out the jet velocity. So jet velocity will come out to be 585.8 meters per second. propulsive efficiency is nothing but 2 into air velocity divided by jet velocity plus air velocity. So substituting that, we can find out jet velocity, and absolute velocity is jet velocity minus air velocity. This is nothing but 585.8 minus 222.2, which will come out to be 363.6 meters per second. So the absolute velocity of jet is 363.6 meters per second. So the next is volume of air compressed per minute. So for finding out volume of air compressed, we need to find out the mass of air which is being compressed, and we know propulsive force or thrust force, which is change in thrust force, which is change in mass. Sorry, this is thrust force. Thrust force is change in again tell propulsive force and thrust force. Mass of air into change in velocity, or the change in linear momentum, that will give me thrust. So that will be equal to the drag force 6100. So from here I can find out the mass of air. So mass of air is 16.77 kg per second. So now mass of air is known. I know the density of air. So this is nothing but mass by volume. So from there I can find out the volume of air. So 16.77 divided by 0.17. So to convert it to minutes, I multiply by 60. So it will come out to be 5918.8 kg per minute. So this is the volume of air which is being compressed. Next is to find out the diameter of the jet. So I know the volume. So straight away you can find out area into velocity. So volume is area into velocity. So velocity here is 585 pi by 4 d square, the jet diameter, into velocity of the jet equals the volume of air. So substituting that, I can find out the diameter. The diameter will come out to be 0.463 meter or 463 mm. So that is the diameter of the jet. The next is to find out power output of the unit. To find out power output is nothing but the thrust power which is generated. That is the power output. Thrust power or thrust work. So which is thrust force into velocity of turbojet. So thrust force is nothing but drag force. So drag force is 6100, which is given, into velocity of air we know 222.2 Newton meters per second. So it will come out to be 1355 kilowatt. So this is the thrust power, and then turbine output or propulsive power is propulsive efficiency is thrust power divided by propulsive power. Propulsive power is nothing but the turbine output which is we are getting. So so that will come out to be 1000. Thrust power is 1355.4. The propulsive efficiency is 0.55. So the propulsive power, so power output is 2464.4 kilowatt. So next is overall efficiency. So overall efficiency is nothing but your propulsive your output divided by the heat input. So heat equivalent output is 2464.4. So divide by mass of fuel into 46,000. So you know overall efficiency is 0.17. So the mass of fuel is 0.1315 kg per second. So now we have found out mass fuel. So air fuel ratio also we can find from this. So air fuel ratio is air used divided by fuel used. So air used is 16.77 kg per second divided by 0.315 kg per second for fuel. It will come out to be 53.24. So the next question is, in a jet propulsion unit, air is drawn into the rotary compressor at 15 degrees Celsius and 1.01 bar and delivered at 4.04 bar. The isentropic efficiency of compressor is 82% and the compression is uncooled. After delivery, the air is heated at constant pressure until the temperature reaches 750 degrees Celsius. The air then passes through the turbine unit, which drives the compressor only and has an isentropic efficiency of 78% before passing through the nozzle and expanding to atmosphere pressure of 1.01 bar with an efficiency of 88%. After delivery, okay, the neglecting any mass increase due to the weight of the fuel, and assuming that R and gamma are unchanged by combustion, determine the power required to drive the compressor. The air-fuel ratio if the fuel has calorific value of 42,000 kJ per kg, the pressure of the gas leaving the turbine, the thrust per kg of air per second. Neglect any effect of velocity of approach. Okay. So this, I think the images are reaching. So this is the curve. So initially compressor from 1, there is no ram effect here. So that's what is assuming there is no ram effect of velocity initially. So state 1, from 1 there is compression. So 1.01 bar, you are compressing it to 4 bar in compressor, and compressor has some efficiency. So from 1 to 2 is the isentropic process. This is following 1 2 dash. After that, you are heating at constant pressure till 750 degrees Celsius to state 3. After 3, you are expanding in turbine, which has some efficiency. So it follow 3 4 dash. After that, you are passing through nozzle to the ambient pressure. So 4 dash 5 dash, and the nozzle has some efficiency. So now that is the process followed. We'll see how to solve this. So initially T1, so T1 is at 15 degrees Celsius. So 15 plus 273 is 288 Kelvin, and pressure is 1.01 bar, and pressure at state 2 is 4.04 bar after compressor. So state 2 is 4.04 bar, and we know that turbine inlet temperature is at 750 degrees Celsius. So converting that into Kelvin will give me 1023 Kelvin. So, and we also know that compressor efficiency is 82%, turbine efficiency is 78%, and nozzle efficiency is 88%. So now referring to figure, so we can the compressor is operating at reversible adiabatic process. So T2 by T1 equals P2 by P1 raised to power gamma minus 1 by gamma. So we substitute pressures. We know the pressures at across the compressor, discharge and suction. So 4.04 divided by 1.01, and we know gamma value 1.4. Substituting that, so the temperature ratio is 1.486. So using this, we can find out the temperature at exit of compressor, which will come out to be 2.88 into 1.486, which is 428 Kelvin. So this is isentropic temperature rise after compression in compressor. Now if the compressor is not ideal, it has efficiency of 82%, in that case it will be the compressor work in isentropic process divided by actual. So T2 minus T1 by T2 dash minus T1. So using this substituting value, you can find out T2 dash, which will come out to be 458.7 Kelvin. So and here in the problem, R value is given as 0.287. So Cp can be used to straight away as 1.005, or Cp is gamma R by gamma minus 1. So substituting that, we will find out 1.004. So Then the question is to find out the power required to drive the compressor. So it's just a change in enthalpy across the compressor. So H2 dash minus H1, or in terms of temperature is Cp T2 dash minus T1. So Cp is 1.004 and T2 dash and T1 we have found out. So this will come out to be 171.38 kilowatt. So 171 kilowatt of power is required to drive the compressor. Now the second part is to find out the air fuel ratio. So air fuel ratio we can find out doing an energy balance across the combustion chamber. So m dot f into c is the energy supply through combustion, equals ma plus mf into cp t3 minus t2 dash across the combustion. So this here the ma plus mf is taken together. You can also, if you do an actual energy balance, you will get ma plus mf cp t3 minus ma t2 dash. So that's how the equation will be. So then substituting that C value and Cp and the temperature values, we find out that the air fuel ratio is 73.1. So the air fuel ratio is 73.1. So the next is to find out the pressure of the gas leaving the turbine at state 4. So to find out that, we know that the work generated, assuming an ideal case, the work generated in this turbine is used to run the compressor. So the compressor work will be equal to the work generated in the turbine. So Cp T2 dash minus T1 will be equals to Cp T3 minus T4 dash. So using that, we can find out the temperature at state 4 will be 852.3 Kelvin. So this is the actual temperature, but to find out pressure, we need to find out the isentropic temperature rise in the temperature in the turbine at the exit. So using turbine efficiency, T3 minus T4 dash by T3 minus T4. So actual minus isentropic work generated. So using this, we can find out the state 4 temperature when the expansion would have been isentropic. So T4 will be 804 Kelvin. So now using an adiabatic process, we can find out, we know the temperature across the turbine, so inlet and outlet, and we also know inlet temperature and outlet temperature, and we know inlet pressure. So we can find out state 4 pressure. Substituting the values, it will come out to be 1.74 bar. So the pressure at state 4 will be 1.74 bar. So the next question is to find out the thrust generated, the thrust per kg of air generated. So we know the temperature at state 4, we know the pressure, and you know jet nozzle exit pressure. So we can find out the jet nozzle exit temperature when the expansion is isentropically done. So reversible adiabatic process, we can find out T5 state temperature as 729.7 Kelvin. So now with the nozzle is not ideal, so it has some nozzle efficiency of 88%. So we can find out actual by ideal. So T4 dash minus T5 dash divided by T4 dash minus T5. So we substitute and we can find out the actual temperature at the exit of the nozzle, which will come out to be 744.4 Kelvin. So now doing an energy balance across steady flow energy equation across the nozzle, we can find out the velocity of the jet So velocity of jet is nothing but 2 times root of 2 times Cp into P4 dash minus T5 dash. So substituting the values, we find out the velocity of jet is 465.5 meters per second. So the thrust generated is Cj, because initially there is no velocity, so 465.5 minus 0 into mass of air per kg. So Newton, so you multiply by 1, or 465.5 Newton per kg of air. So moving on, the next question is, air at 7 degrees Celsius enters a turbojet engine at a rate of 16 kg per second and at a velocity of 300 meters per second. Air is heated in the combustion chamber at a rate of 15,000 kJ per second and it leaves the engine at 427 degrees Celsius. Determine the thrust produced by the turbojet engine. So now there's a hint given that you have to do a control volume. The entire engine has to be taken as a control volume. So we assume that the aircraft which is there is moving at velocity of 300 meters per second. So this is the engine. So if you do put a control volume across it, so what you can see is the air is entering at 300 meters per second at 7 degrees Celsius and 16 kg per second, and which is coming out at 427 degrees Celsius. So air is heated in the combustion chamber at rate of 15,000 and it leaves the engine at 427 degrees Celsius. So the jet temperature is 427 degrees Celsius and you are supplying heat of 15,000 kilojoule per second across the control volume. So this is what is known. So now converting, we know T1 is at 7 degrees Celsius. So writing it in terms of Kelvin is 280 Kelvin. So the enthalpy will be close to 280.13 kilojoule per kg, and same at state 4 is 427. So 427 plus 273 will be 700 Kelvin, and enthalpy at state 2 will be 713.27 kilojoule per kg. So now if you apply steady flow energy equation across this engine, so energy in minus energy out is the energy stored in the system. So energy, because this is a steady flow, so the energy system will be 0. There is no energy stored in the system. So energy in coming in will be going out. So if you say water coming in, heat is coming in, Q in, plus some enthalpy plus velocity, which has velocity, so it will have some kinetic energy. So m dot into h1 plus v1 square by 2. So this is what is coming on, and there is some enthalpy and kinetic energy possessed by the exit system. So that is E out, m dot into h2 plus v2 square by 2. So now we can take m dot into h1 plus v1 square by 2 to the right hand side. So q in will be m dot into change in enthalpy and change in the kinetic energy. So from this we can find out the velocity at state 2. So applying this equation and substituting the values, we get that velocity at state 2 is 1048 meters per second. So now we have found out the velocity at point 2. Now we can straight away find out the thrust. Thrust is nothing but the change in linear momentum. So m dot into v2 minus v1. So it will come out to be 16 into 1048 minus 300, which is nothing but 11 kilonewton. It's 11.9 or 12 kilonewtons. So moving on, next problem is, a turbojet aircraft flies with a velocity of 1100 km per hour at an altitude where the air temperature and pressure are minus 35 degrees Celsius and 40 kilopascal. Air leaves the diffuser at 50 kilopascal with a velocity of 15 meters per second. So air leaves the diffuser at 50 kilopascal. So you know inlet air which is coming in and the exit of the diffuser. So exit of diffuser is 50 kilopascal and 15 meters per second. And then combustion gases enter the turbine at 450 kilopascal and 950 degrees Celsius. The turbine produces 800 kilowatt of power. The turbine work is given, all of which is used to drive the compressor. Assuming an isentropic efficiency of 83% for the compressor, turbine and nozzle, and using variable specific heats. So using variable specific heats, so what we do is we'll take the values from the straight away from the ideal gas table of the air. So instead of assuming Cp as constant and assuming enthalpy is just a function of temperature, so we can find out straight away values, enthalpy and everything from the table, just like what we did in the previous week. The previous week problem I solved everything. Most of it is from the using the tables. So we took values all from the tables. So similarly, we will do this problem. So till now, in the previous problems, we assumed that the air is ideal and your specific heat is constant, so it's not varying with respect to temperature. So that's not the case here. So here you have specified that using variable specific heats. So next is determine the pressure of combustion gases at the turbine exit, the mass flow rate of air, and then the velocity of gases at the nozzle exit, and the propulsive power and the propulsive efficiency for this engine. So we'll see how to solve this. So initially, first the process is across the diffuser. So this is the process. 1 to 2 is the diffuser, and 2 to 3 is the compressor, 3 to 4 is the combustion chamber, 4 to 5 is your turbine, and 5 to 6 is the nozzle. So this is the process, and assume this is for an ideal case. Similarly, this is here we have an non-ideality. So we'll see. So across the diffuser, your inlet temperature is minus 35 degrees Celsius. So correspondingly, the enthalpy for that is 283.36 kilojoule per kg. So now when we apply a steady flow energy equation across the diffuser, we'll get H1 enthalpy 1 at inlet plus V1 square by 2 equals enthalpy at state 2 plus V2 square by 2. So substituting, so we know aircraft velocity is 1100 km per hour. So we can know velocity at state 1, the air velocity, and we also know that velocity at exit of the diffuser is 15 meters per second. So 1100 kilometers per hour, you have to convert into meters per second. So 1100 divided by 3.6, or 1100 into 1000 divided by 3600. So substituting that values, and we can find out H2 enthalpy at state 2 as 284.93 kilojoule per kg. So this is the enthalpy at state 2, and we know the pressure at state 2 at the exit of diffuser is 50 kilopascal. So inlet is 40 kilopascal and the exit of diffuser is 50 kilopascal. So for state with pressure 50 kilopascal and enthalpy 284.93 kilojoule per kg, we get that entropy at point 2 is 5.8513 kilojoule per kg. So now assuming initially that the compressor is an isentropic compressor, we can find out that enthalpy at state 3, we know that the compressor is compressing to 450 kilopascal because the turbine inlet temperature is at 450 kilopascal. So 450 kilopascal and entropy of 5.8513 kilojoule per kg, we get enthalpy as 534.42 kilojoule per kg. So this is assuming an isentropic compressor, but the compressor has efficiency of 0.83. So your isentropic work divided by actual work. So compressor efficiency is 0.83, which will be equal to 534.42 minus 284.93, which we have already calculated. So the enthalpy at state 3 will come out to be 585.52 kilojoule per kg. So now we know that the work which is generated in the turbine, which is used to run the compressor. So the compressor work will be equal to the turbine work. So H3 minus H2 is the compressor work, which will be equal to H4 minus H5. So, and we know that temperature at 4 is 950 degrees Celsius and 450 kilopascal. So So correspondingly, the enthalpy at state 4 will be 1305.2 kilojoule per kg. Now substituting that, we'll get the enthalpy at state 5 is 1004.6 kilojoule per kg. So now this is we know 4 and 5. To find out pressure at state 5, what we do is similarly we use the turbine efficiency to find out the isentropic enthalpy change to state 5. So enthalpy at state 5, if you expand it isentropically in the turbine, it will come out to be 943.04 kilojoule per kg. So now we know the temperature and pressure at state 4. So the corresponding entropy is 6.7725 kilojoule per kg Kelvin. So using this entropy and enthalpy, we can find out pressure is 136.9 kilopascal. So we know the pressure at the exit of the turbine. So we can calculate the now to find out mass flow rate. So to find out the mass flow rate, we know that the turbine produces 800 kilowatt of power. So we can use the turbine work, or that will be equal to the compressor work. So m dot equals to compressor work divided by H3 minus H2. So 800 kilojoule per second divided by the enthalpy change will come out to be 2.661 kilojoule per kg, kilograms per second. So this is the mass of air which is passing through the compressor. The turbine, it will be MA plus MF. So okay, then in the nozzle we know state 5. So assuming that nozzle there is an isentropic efficiency, isentropic process. So at state 5 we know the entropy, we know the enthalpy and corresponding pressure. So for 136.9 kilopascal and enthalpy of 104.6 kilojoule per kg, we get entropy of 6.8382. So for same entropy and the exit pressure of 40 kilopascal, we find out the enthalpy as 713.12 kilojoule per kg. So now the nozzle also has an efficiency of 83%. So the actual exit enthalpy is 762.68 kilojoule per kg. So now when we do an steady flow energy equation across the nozzle, we can find out the velocity at exit. The jet velocity then will be 695.6 meters per second. So now we have found out the jet velocity. Now we can find out the propulsive power. So it is equal to m dot v6 minus v1 into that is the thrust into the air velocity. So we know all the values. On substituting, we get the propulsive power as 317.2 kilowatt. And now the energy supplied is nothing but H4 minus H3, because we don't know anything about fuel. So we'll use this value and assume that combustion efficiency is 100%. So H3 minus H4 into m dot will give me the energy supplied. So m dot is 2.661, which we previously calculated. So into H4 minus H3, so this will give me 1915 kilowatt. So the propulsive efficiency is the propulsive power divided by the heat supply. So 317.2 kilowatt divided by 1915 kilowatt will come out to be 16.6%. So we have found out all which is required. So these are some numericals which we saw how to solve. So most of it is the major parameters which are asked to be found are your propulsive efficiency and the thrust parts. So these are the major important values, and the rest of it is you can directly use apply in steady flow energy equation, and if you know the process using that you can find out all the values, and you have to use just the steady flow energy equation to find out enthalpies and temperatures to find out the works and the jet velocity, and using that if you have the velocity, inlet velocity, outlet velocity, and the mass flow rate, you can find out all efficiencies and the thrust bars. So that's all for the jet engines. So this ends the module on the gas power cycles. So next week that will be on refrigerations. So we'll see numericals and problems on refrigeration. Thank you.